Hi, welcome to part 4 of the Accuphase P-300 restoration. In the last video we left off with a fully functional amplifier, so the protection circuit was resolved and we also repaired the damaged output section of the right channel and tested with the original driver cards. So what's left to do on this is the driver cards. I was originally just going to replace some capacitors, but after looking at the service bulletins there's a lot of transistors that are also recommended, so I'm going to upgrade the driver cards to the recommended service bulletin spec, and then also do some work on the meter circuit, which should be pretty simple. But before we do that, I'm going to take off the front panel and thoroughly clean all the controls, and I'd like to get some base measurements of distortion and frequency response to see if any of the changes done to the driver cards change the performance of this amplifier in a good way. So one of the unique things about this, because it's a card-based design, I'm going to be able to pull a card, work on it in steps. So I'm going to first replace the trimmers, then the capacitors, and then transistors in bunches to see if any of those replacements make changes in specific areas. So if that sounds cool, stick around and we'll get started. Alright, so I'd like to start with a frequency response test to get a baseline here. So this unit is supposed to operate at from 20 to 20 kilohertz with only 0.2 dB deviation, which means if you look at this in graphical formula of a flat frequency response all the way out to around 20K, and then it'll start to dip. What I'm seeing here is a little bit different. So what I have happening right now is I'm feeding a sine wave into the amplifier, and then I'm outputting into an 8-ohm dummy load and measuring about 2.83 volts, which is about 1 watt. So I'm trying to duplicate this measurement here, this 1 watt frequency response. So this is at 1 kilohertz. I'm going to take these down into dB mode. So I'm going to set this as my 0 point here. And then if I take the frequency and I drop it down, we're now at 400 hertz, 300 hertz, 100. And we can see that this sine wave is staying pretty consistent, maybe increasing by 0.1, 0.2 dB, but overall very flat. Let's go back up to 1 kilohertz. And I'm going to take this up in 1K increments. So now we're back to 0 dB. But even as I start getting up 3, 4, 5, 6, you can see the sine wave shrinking and my deviation going up. And we're already 2 dB out at this point. So I'll take it to 20 kilohertz. And I'm almost 3 dB down at 20 kilohertz itself. So the roll-off is happening earlier than the spec sheet is saying. If we look at this in another way, if we do a 1 kilohertz square wave, this wave should be, squared off there if you have completely flat frequency response. In this case, this wave is showing us what we saw with the sine wave sweep, in that the frequency response is dipping when it gets up into the higher frequencies. So that's the performance of the amplifier in its current state. Next I'm going to measure some distortion levels, and then later on we'll work on the boards and see if any of this changes when we start changing some parts. Next up we're going to be taking a look at the THD spec on this. So at rated power, at any frequency, it should not exceed 0.1%. It's from quarter watt all the way up to rated power, I guess. And then the distortion curve looks something like this. So at 1 kilohertz, we're kind of at the bottom end of where the distortion should be, so that's where I'm going to measure at full rated output power. So I'm going to turn on my low distortion oscillator. We've got about 34.7, 34.8 volts here in RMS. That translates to the rated power of 150 watts per channel. Sine wave is looking nice and clean. I've got both channels overlaid right now. So we'll flip these into THD+N. We're at 0.04%. I'm just going to sweep this with the oscillator.
about 2 kilohertz. $3K. So we're approaching that spec right now and now exceeding it. So once I get past, about 3 kilohertz, it's looking like we're not meeting the distortion spec. I'm going to take this down. Sorry, my dummy load is kicking in. That's the fan there. This is running at 150 watts, so you can imagine. All right, we're going to go down to, oops, wrong way. It's like we're at 20 hertz. You can see the distortion goes way down when we meet the lower frequencies there. Let's give another point here. All right, I'm going to shut this off, so finish that test. So at 150 watts, the distortion seems to, let's see if it tracks this curve. It's actually a little bit different. What we're seeing is that the distortion drops as we go to lower frequency, and it goes, actually this is showing it increasing at 3. It's just we're going a little bit above that 0.1%. So I'm going to clean all the controls in this thing. Sometimes that helps with the distortion level. So I'm going to clean all the controls and retest, and then we'll start working on some of these cards. After cleaning all of the controls, I found that I still had a little bit of noise in the filter and the input selector switch, and I removed them to check them out. And what I found is that there's a point I needed to unscrew a little terminal strip in order to get this switch out. And with some testing, I found some weird results when working with this, so I may have an issue with my chassis ground. So I'm going to show that on the scope so you get an idea what I'm talking about here. So I've got the unit powered on, and that terminal strip point I just have a clip lead tied to. If I just grip it onto part of the chassis, we can see already that our waveform is improving. And if I switch into a sine wave here, I'm going to ramp this up to, see we've got a much flatter frequency response. I'm already at 9K and it's barely dropping. When I get up to 20K, looking at my meter here, where we had negative 3 dB before, I'm at negative 1.2 dB. So already a major improvement just from cleaning the switches and kind of manipulating this area here. Now if I go back to the square and I remove this connection, see a lot of weird things. If I take this connector and just probe around different parts of the chassis, I can improve the square wave, and then certain parts I get a lot of ring. So I'm definitely onto something here. So I'm going to dig a little bit further into this and see if I can get it to be, stable like that waveform there, and then we're going to have much better frequency response. Okay, now that we've got some of those control issues sorted out, I'm going to redo the frequency response test. So I'm at 2.83 volts again. Take this into dB mode. And I did change one other thing on this signal generator. I'm not sure if there's some sort of relationship with the input impedance of the Accuphase. I'm getting much better results with the Tektronix oscillator. So this is a low distortion oscillator that is purpose built for doing one thing, and that's creating perfect sine waves. So we're going to use this for the test, and I think we're finally at the point where we're meeting the spec sheet here. So right now I'm at a 2 kilohertz sine wave, and I've set my 0 dB reference, and I'm just going to sweep this. And if we look up here, we have very little change. Now at 3 kilohertz, 4, 5, that's 10 kilohertz there. On this channel we do have a little bit of a deviation. Let's see, where am I going here? I'm trying to get down to 20K. That's 20 kilohertz there. I've got negative 0.2 dB and negative 0.4 dB. So very, very close. We may be able to resolve this with some of the transistor modifications on the main driver board. So the frequency response is now matching up to this 1 watt curve, where I have very flat response all the way through the range. I guess we can go down to the bottom end too. Let me take this right now. We're at 2. This is 20 hertz here. Looking good. It's 40 hertz. Yeah, so really good frequency response now. This is looking great. Next up, we'll repeat that distortion test. The first time I looked at this graph, I misread it. I interpreted it as frequency versus THD, but it's actually output power versus THD with 3 frequency points. So while I've got this set up for 1 watt, I'm going to test this point here, which should be one of the lowest distortion points in the amplifier's operation range. And instead of testing at 1 kilohertz, I'm going to change to 2 kilohertz so that I can easily do a 10x toggle on the oscillator. So right now we're looking at the THD for the 2 kilohertz signal. So we got, about 0.04% up, or sorry, 0.04%, 0.05%. So it doesn't quite meet that bottom level on the curve, but we're well within that, spec of no higher than 0.1% throughout the whole operating range. So that's 2K. Let's go up to 20K. Much better than before. We'll see if this matches up on the full output power test. And then let's go down to 20 hertz. All right, okay, I'm gonna set up for a 150 watt test and we'll repeat this. So for this test, we are in between the 100 and 200 watt mark on here. So you can see that's gonna be much elevated from where we tested down here at 1 watt. So I'm going to set this at level here, turn on the oscillator, right around that 150 watt mark. Switch into THD. So again, this is at 2 kilohertz, 0.07%, so well within spec. And then we're going to go up to 20 kilohertz. Higher, but still not up to that 0.1% and exceeding like we saw the last time we did the test. So I have a little confession to make here. In the last series of distortion and frequency response tests, the right channel had already been modified. So what you noticed there in those tests is that when we ran sine waves and square waves, everything was identical channel to channel. The modifications I've made here made very little difference to the way that the waveforms looked on the scope. Now, the reason this happened is because troubleshooting is not always linear. So I was chasing a frequency response and distortion issue, but I was on track to rebuild these cards anyway. So as part of that process, I started replacing some components and testing in stages, channel to channel, and throughout that I saw very little change. That's what eventually led me to take a closer look at those filter and input selector controls. So in those tests, you may have noticed the right channel had slightly lower distortion in the mid and top frequencies, and that was this guy here. So it's completely possible that some of these transistor changes have made an improvement in THD. So what we'll do is get this channel also reworked to match this one, and then we'll repeat those tests. Now, what I've got going on here so far is I've replaced the DC offset trimmer, and it made little difference. It's easier to adjust, but it's not, it wasn't going to change anything with the sound quality. Then we have, this is part of a service bulletin mod, which I'll show here next. So the reason I did this service bulletin mod is this note here, basically saying that if you have an old version, old production unit, this mod should definitely be considered. So they have a list of transistor substitutions. This is the originals that I had in mind, and this is what they had issued back in the late 70s, early 80s, whenever this service bulletin came out. Looks like, yeah, 1976. These were the transistors that they wanted you to change out. Now, these are long since obsolete, so I had to find subs for this transistor, which is what we have in here now. So I completed that transistor replacement. There's also 4 resistors that need to get added in the place of some diodes. So that was these 4 diodes here have been replaced with 4 resistors, and then a capacitor also needs to get moved. This guy here gets flipped to the back of the board in an alternate location. And if you get a newer unit, this will have already been done, but on this old serial number, none of these modifications took place. So I'm trying to bring this up to the the recommended service bulletin spec. So next up, I'm going to get this board looking like this one, and then we'll do another distortion test and see if the channels match instead of the right channel being slightly lower distortion than the left. Okay, both boards are now rebuilt to the same specification, so we're going to throw these in the chassis and see if the performance is now equal. And then there's one more service bulletin that I may do, which is a recommendation to replace some of the transistors in the beginning part of the circuit here. Now this service bulletin doesn't come with that warning, like all older units should have this done like the other one did, so I may skip that depending on the test results. So let's throw these in and see what happens. Okay, I'm now running both channels at the 1 watt level again. I already tested this at full output power and the measurements were nearly identical, so no need to repeat that. But when we're at that 1 watt level, our left channel has come down from about 0.05 and it's actually performing a little bit better than the right channel now. So that transistor change actually did make a difference in distortion level. Let's go up to 20K. Similar to where it was. This is 200 Hertz. And 20 Hertz. But anyways, it's looking better, so matching up those channels definitely did help. That's great information. And just because there was such an obvious and measurable improvement in distortion by changing out those transistors, I think I'm going to do the same thing with the small signal transistors and see if we can get this distortion level down even further.
All right, just when things were going really well, something had to happen. So I got these replaced and I put it in and was testing, and this channel, sure enough, distortion was even lower. I was doing a full output power test, just ramping up one of these front panel controls, and I noticed a spark back here in the corner and some smoke. And I think the failure that initially happened on this channel happened again in the same exact way. So I'm gonna have to dig into this and see if we lost these driver transistors and diodes and stuff, just like we did the last time.
Okay, so obviously I was a little bit disappointed when I saw that spark in the back of the chassis and this amp channel failed again in a very similar manner to the error state that it was initially in when I got the amplifier. But I'd much rather have something like that happen here at the bench rather than you know, at a client site after somebody has got a restored piece back. So I'm going to get this resolved, and it's possible we'll even get better performance out of the channel after this is repaired. So the first time that this happened, when I got the unit and powered it up for the first time, I had some shorted output transistors. These 4 diodes were all shorted, these drivers were shorted, and one of each of the output transistors was shorted. I went through this board here and I checked all of the resistors. There's not many parts on here, it's just a bunch of resistors, a couple caps, and a coil. So I checked everything and everything was okay. But this time the failure was more widespread in the amplifier channel. So I lost 2 outputs on one half and 1 on the other, and I lost all 3 emitter resistors on this side of the amplifier. So that's these little 1 ohm, I think 3 watt resistors. There was a lot going on with this. I mean, I was changing a lot of components. I was testing at high power for extended periods of time. So there was many variables here. So I'm just going to do my best to try to figure out what may have happened, address as much as I can, and then I'll definitely be doing a lot of stress tests on this amplifier. I'm planning on keeping this one for myself for probably at least a year or 2, just because it was such a cool design and I'd like to listen to it a bit in my system. So I'll, you know, run this one through all its paces well before it ever gets sold. So everything was stable up until I replaced these. Now, this could just be a coincidence. These parts are very high quality. I matched them channel to channel, matched them to each other. That shouldn't be a problem there. This may have been an issue here. That is the trimmer for the bias. Sometimes these can get scratchy and cause jumps in the bias, which can take out output stages. It's been stable up to this point. I had a couple, you know, jumpy points during the rotation, but nothing, you know, while it was sitting in set where it would jump around. But it's definitely possible that this old bias VR is having some trouble, and the replacement part did come in, so I'll be addressing that on the driver board. I don't think I need to do anything else there. And I have already loaded the one that blew up this channel. I loaded that into the other side and it's fine. So I think, again, the driver card's okay, and it was something on this side. So one of the other things that I noticed when I replaced the diodes over here the first time, I know for a fact I followed this orientation here for the diode placement. But this time, when I took these out to replace them again, I noticed that there was a alternate diode symbol that's kind of drawn on with black paint on the other side of the PCB, and the anode and the cathode are reversed. And I think it was supposed to go in this way. I checked my other channel and its diodes followed the orientation that's written on this side of the board, not here. And I found some detailed high-res images of another person that was working on one of these. Theirs was a little bit of a later version, and it looks like Accuphase corrected that silkscreen error. So it's quite possible that I had a couple of the replacement diodes installed backwards. And yeah, so I've got a few things that that need to get addressed. I need to replace those 3 emitter resistors. There was also a 33 ohm resistor in that same area that failed. That was this one here. So I'm going to replace any resistors that failed. The diodes are already in. I'm going to do new production output transistors. I have some on-semi transistors that I'm going to use instead of trying to source more new old stock parts. I got really lucky the first time. So I've got another set of new old stock drivers that just came in, and then this will all be modern production on semi on the replacement. So hopefully when everything's back up and running and we compare channel to channel, I'll get the best results out of the fully rebuilt driver card and the new silicon output transistors. If that's the case, I'll definitely rebuild the other channel with the on semi parts, and then we're off to the races. So I guess in the next shot, I should have this reassembled and we'll be back up and testing again. All right, so I've got this output board rebuilt, new emitter resistors, all new output transistors. So this is back up and running, and I did also get my replacement VR installed here for the bias. When I went back to test this again, I noticed some pretty strange things which I want to show you. So I think the reason that this originally failed was due to oscillation, possibly to do with my Tektronix signal generator. So right now I've got the unit plugged into the Tektronix SG505 at kind of a low signal level, and I'm just going to use the front panel controls in the Accuphase to bring these up. So left channel, fine. Right channel is fine by itself, but if I take this one up to max, and then the other one, right as I approach the maximum of the volume control, I get oscillation, and that happens consistently on any level of the oscillator. So I think that may have been the original cause of the problem, because I was testing at a really high output level, and it probably sent this thing into oscillation and just one channel blew before the other. So just to demonstrate this, I'm going to connect the amp to this signal generator instead. I'm just going to power off here and switch these connections around. Okay, I'm now plugged into the Siglent generator here. Power back up. And I'm at about the same, output level. I'm at 170 millivolts peak to peak, so I can raise this up a little bit. We're probably getting somewhere around there out of the Tektronix. So that's left control maxed out, and right control maxed out, no oscillation. So all things equal, cable and everything, for some reason on the Tektronix oscillator, something is going strange when I have the volume control at maximum. So I'm going to continue testing with the Siglent. I will be able to use the Tektronix for now. I just have to make sure that my attenuator is set so my signal is really high, so I don't have to max out the volume controls. So eventually I do need to look into this oscillator. I might have to replace some parts in that. So I'm going to move on from here, get the other channel new output transistors so that they match. So I've still got to do this channel, and then we'll do some final testing and see where we're at. Okay, we're at the 1 watt level test. I've got the same output transistors on semi fit into both channels. You can see our distortion level is the lowest it's been yet. I had to increase the level of the attenuator a little bit, which allowed me to operate in a lower range with these volume controls, and this is how I was able to get this measurement down below about 0.03. So this is the best that it's been performing so far. So this is with all the new transistors in the driver boards and the outputs. Let's go up to 20K. Still under that 0.1% comfortably. It's 200 hertz and 20 hertz. So that is the lowest distortion level I've been able to get on this yet. I'm happy with this outcome here. I'm going to end this video here, and the next time we will be looking at the final thing that I need to do, which is main filter capacitors. There's yet another service bulletin mod to address these because the working voltage is too low compared to what the DC output of the power supply is going to be doing with modern mains voltages. And then we'll do a quick meter calibration, and this thing should be ready to rock. So thanks again for stopping by the channel. Please subscribe if you like this content, and watch out for the next video coming soon on the main filters and the meters.